All right, welcome to module number 17. In the previous module, we started discussing data structures. We talked about stacks and queues, and then we talked about linked lists, singly linked or doubly linked. And the linked lists were a bit more complicated than the stacks and queues because all of a sudden we could insert something anywhere in the list. Whereas with the stacks and the queues, we had either a last in, first out, or first in, first out order. So let's say in the stack, it's a stack of dishes, that's the analogy, and you always put the new plate that you're receiving, the new dish, on top of the stack. And in a queue, a line of customers, the new person is always end of the line. Whereas in a list, you have more flexibility. Similarly, graphs and trees are offering more sophistication. And the trend here, as always, is trade-offs. To do more powerful things, to have more complicated relationships between objects in our data, we need more sophisticated types of data structures. So we're beginning with graphs, and the next module is going to be trees. A graph is a structure that relates between different objects. A typical notation is going to be G as a function of V and E. G is for graph. The V is a set of vertices. Vertices are also known as nodes. So you can say that A and B are both elements of the set V. And overall, the set V contains the elements A, B, C, D, E. And the graph G, in addition to containing V, the set of vertices, nodes, it also contains E, the set of edges, and edge connects between two vertices. Now this could be a directed graph, meaning that edges are arrows, and it could also be an undirected graph, such as this example, where an edge is, you would think of it as bidirectional. So some concepts here. Consider an edge connecting two vertices U and V. So we say that UV in parentheses is an element of the set E of edges. Again, lowercase u and lowercase v are elements of the set capital V of vertices. And we say that V is adjacent to U. Now, in an undirected graph, U and V are adjacent to one another. In a directed graph, V is adjacent to U, but not vice versa. The next concept is the degree of V. That's the number of edges that correspond to connect to a vertex in V. So if we're looking at this graph, and let's look at the vertex E, the degree, and I'll just write DEG for short, of the vertex E, so let's count this. We have one edge to A, another edge, number 2 to A, a third edge to C, and a fourth edge to D, so the degree of E is 4. All right, what about a path? Suppose that U and U prime are vertices in capital V. We have a path of length K denoted by P for path, if the following conditions hold. So V0 connects to V1, V1 connects to V2, V2 connects to V3, and so on, up to Vk minus 1 connecting to Vk. So overall, how many edges were in this path? From 0 to 1 is 1, from 1 to 2 is 2, from 2 to 3 is 3, from K minus 1 to K is K. We have a length K path. The first vertex is V0. The last vertex is Vk. So if V0 is equal to U and Vk is equal to U prime, then we have a path from U to U prime. And there's one more thing that we need to verify. We had a list of edges, but we must confirm that they actually exist. Each of these edges from Vi minus 1 to Vi must be an element of the set of edges capital E. If all of these conditions hold, then U prime is going to be reachable from U using path P of length K. For example, let's look at a path. We start at D, we go to E, that's the edge DE. Then from E to A, the edge EA, and taking their combination, we went from D to A. That's a length 2 path. More about paths. A simple path is a path such that all the vertices on the path are distinct. Distinct meaning that you don't have the same vertex appearing twice. All the nodes are different. And if a path is not distinct, that means that we can shorten the path. So imagine that we have this path, okay, from B to C, from C to D, from D to A, from A to B, from B to C again. Well, we could go from, let's change color, we could go from B to C directly. And this traversal from C to itself, or well, from B to itself, it was redundant. So a simple path doesn't contain these redundancies. Now what about a cycle? A cycle, we've just seen cycles from B to B and from C to C. We have a path that starts and ends at the same vertex. So let's look at an example. One cycle, P1 for path 1, begins at the vertex A. So we're at A. We then move to B. Now we're at B. We move from B to C. We move from C to A. And that's a cycle from A to itself. What about P2, path 2? We go from A to C, and from C back to A. Both of these are two different cycles that begin at A and end at A. So as you can imagine, there are many graphs that do have cycles, but some graphs don't have any cycles at all, and they're called acyclic graphs. They may have some advantages, meaning that there's less redundancy. If edges are costly, for example, a road network, you don't want 70 times more roads than is necessary. But on the other hand, having a small number of redundancy is helpful. So for example, imagine that there's only one road from Raleigh to New York, and if there's a traffic jam anywhere, it can be in Washington or in Philadelphia or anywhere on that road, you're in trouble. And if you have a road network, that it's not necessarily, you don't have roads between any two cities, but you have roads between adjacent cities and a few more. In that case, you have redundancy in your road network, and a modest amount of redundancy can build you a lot of robustness. So connectivity in graphs. We just talked about paths and we talked about cycles. So when we have undirected graphs, if you have a connected component, that means that you have a set of nodes that all the nodes are reachable from one another. Let me try to illustrate that. So you'll have, let's say, 4 nodes, and here it suffices to have 3 different connections, and you can go from A to B to C to D. You can go from D back to A, while at it, D goes to C, D goes to B also. So all the connections are here. So connected component in an undirected graph means that somehow all nodes in that connected component are reachable from one another. Connected components partition the set of vertices into equivalent classes. So what's an equivalent class? So let's say that this is E and this is F. It means that we have a set that within that set we have multiple classes. Each of these classes is a connected component. They're all reachable from one another. But if you take any 2 classes, any 2 vertices in class 1 or class 2, let's change color. The first example was class number 1. The second component was class number 2. In our equivalent class, any node in class 1 is not reachable with any node in class 2 and vice versa. So that's a connected component. And what if there's only one connected component? That means that everything is reachable everywhere, and that's called a connected graph. So that's the concept of connectivity in an undirected graph, but we also have concepts of connectivity in directed graphs. A strongly connected graph is a situation where all the nodes are reachable from one another using directed paths. The indirected path, so this would be A, and this would be B, and let's say this would be C. If there are arrows from A to B to C, then through this cycle, any of the three nodes can reach any of the three nodes, and it's strongly connected. On the other hand, again, this is a directed graph, and it could be all you have to do to make it unconnected is you change the directions of any of these guys, and now instead of, and I'll do this in color, instead of C pointing to A points to C. You can go from A to B, you can go to A to C, you can also go from B to C, but once you reach C, you're stuck. So that's no longer a directed graph, or rather that's a directed graph, but it's not strongly connected. A complete graph is a graph where all the vertex pairs are adjacent, meaning that any pair, you have an edge. As I said earlier, that type of graph is going to be very cyclic, very redundant, but in some applications there are advantages. Finally, the last topic that relates to graphs is a bipartite graph. This is a graph where the set of vertices can be partitioned into two sets of vertices, V1 and V2, and every edge in our set capital E will go from an element of V1 to an element of V2, meaning that if we have an edge UV, either U will be in V1 and V will be in V2, or vice versa. U will be in V2 and V will be in V1. So you never have connections inside V1 or V2. We always have connections between the two. Now here's an application. So imagine that you have a linear regression problem, y equals xb plus epsilon. We'll talk more about this problem later in the course. So y is a vector, x is a matrix, beta is a vector, and epsilon is another vector. So we can solve this graph as follows. Details appear in a paper by myself, Sriram Sarvatam and Rich Baranuk. V1 is going to correspond to the y's. You can think of y's as noisy measurements. What about the betas? The betas are the variables that are unknown, and we're trying to estimate them. Our overall goal, given y, the noisy measurement, and x, the matrix, we want to estimate beta, okay? So we're going to arrange the y's in V1, the betas in V2. The matrix is going to correspond to edges E, meaning that if there's a location in the matrix between a node in V1 and another node in V2, so every location in the matrix has its correspondence, and I think that you saw this in the project that we have about group testing, and this edge, which corresponds to a matrix element, may have properties. For example, in our project, we either measured or did not measure 0 or 1. A more complicated type of X matrix may have different numbers, not just zeros and ones, but also different types of numbers. Our goal is to estimate beta by passing messages between V1 and V2. And in other communication signal processing applications, bipartite graphs are also used in estimation types of procedures. So that'll be all for this module, and we'll continue next time.